Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the earliest moments of Earth's solid surface, back to a time when the ground beneath our feet did not yet exist, when the planet wore only molten skin. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The Earth is young. 4.5 billion years have not yet passed since dust and ice coalesced in the solar nebula. Since gravity drew matter inward and compression ignited heat, the planet exists now as a sphere of layered fire, iron sinking toward the center, silicates rising toward the surface, and everywhere, motion. There is no crust yet, no solid ground, only an ocean of liquid rock, glowing red-orange beneath a sky thick with carbon dioxide and water vapor, convecting in cells hundreds of kilometers across. The surface temperature hovers near 1,200 degrees Celsius. At this heat, basaltic rock flows like honey. Olivine crystals drift suspended in magma currents, and nothing remains rigid for long. The Hadean Aeon earns its name from the Greek underworld. Though no flames exist here, only radiant heat and the slow churn of planetary differentiation. The young Earth breathes out its primordial warmth into the vacuum of space, cooling by fractions of a degree per million years. Patient, inexorable. Above the molten surface, the atmosphere presses down with perhaps 10 or 20 times the pressure of the modern sky. Carbon dioxide dominates, with nitrogen, methane, and vast quantities of steam. The greenhouse effect is extreme. Heat cannot easily escape. The planet traps its own warmth beneath this thick atmospheric blanket, slowing the inevitable transition from liquid to solid. It will take tens of millions of years, perhaps 100 million, before the first stable crust can form and persist. The boundary between the molten surface and the atmosphere is not sharp. Gases bubble up through the magma ocean, releasing volatiles that have been trapped since the planet's accretion. Water vapor rises, only to condense in the cooler upper atmosphere and fall again as superheated rain that evaporates kilometers before reaching the surface. A hydrological cycle operates, but it touches nothing solid. The rain becomes steam. The steam becomes cloud. The cloud becomes rain. Around and around, never resting on stone, convection cells within the magma ocean create transient topography. Hotter, less dense rock rises in broad plumes, spreading horizontally when it reaches the surface, then cooling and sinking again at the edges. The surface undulates with these motions, hills and valleys of liquid stone, features that exist for centuries or millennia before dissolving back into the general flow. Nothing is permanent. Everything moves. The young moon hangs in the sky, enormous. It orbits perhaps 20,000 kilometers above the Earth's surface, 15 times closer than it does today, formed perhaps only a few million years earlier from the debris of a Mars-sized impactor. The moon exerts powerful tidal forces on the molten planet below. These tides do not move water. There is no liquid water yet, but instead flex the magma ocean itself, creating bulges of molten rock that follow the moon's orbit. The Earth's rotation is rapid, each day lasting only 5 or 6 hours, and the tidal bulges race across the surface in a rhythm of stone. Took 100 million years just to cool enough for the first solid pieces to form, not exactly rushing, deeper within the planet. Differentiation continues. The iron catastrophe, the name geologists give to the sinking of metallic iron toward the planetary core, releases enormous quantities of gravitational potential energy as heat. This heat sustains the molten state of the surface, even as the outer layers try to cool. The nickel-iron core grows. The silicate mantle stabilizes in composition. Slowly. The planet sorts itself by density, and this sorting is what will eventually permit the formation of a crust less dense than the mantle beneath it. Radiogenic heat contributes as well. Uranium-235 and uranium-238, thorium-232, potassium-40. These isotopes decay within the Earth's interior, releasing energy. In the Hadean, radiogenic heating is perhaps 3 times more intense than it is in the modern Earth. The planet is fundamentally hotter, more active, more turbulent. The magma ocean persists not only because of residual accretionary heat, but because the Earth continuously generates warmth from within. And yet, despite all this heat, the process of cooling has begun. Heat radiates into space. The outer layers of the magma ocean begin to crystallize, forming a thin, unstable skin of solid rock. But this skin is fragile. Convection from below breaks it apart. Denser minerals sink. Lighter minerals float. The skin reforms, breaks, reforms again. For millions of years, the surface oscillates between partially solid and entirely molten, never quite committing to one state or the other. The composition of this proto-crust matters. The first minerals to crystallize from a cooling basaltic magma are olivine and pyroxene, dense, magnesium-rich silicates. These minerals are heavier than the remaining liquid, and so they sink, leaving behind a melt that is progressively enriched in silica, aluminum, sodium, and potassium. This process, called fractional crystallization, is the first step toward creating the lighter, more buoyant rock that will eventually form continents. But it is slow. So slow. Took longer to make the first granite than it takes for entire mountain ranges to rise and erode away today, just forming a recipe for buoyant rock, millions of years for a prototype. Scientists do not know exactly when the first stable crust formed. The rock record from the Hadean is almost entirely absent. Erosion, subduction, and metamorphism have destroyed nearly all direct evidence of the planet's first 500 million years. What remains are a few dozen zircon crystals, tiny grains of zirconium silicate, each smaller than a sand grain, found in much younger sedimentary rocks in Western Australia. These zircons crystallized between 4.4 and 4.0 billion years ago, and their chemistry suggests they formed in the presence of liquid water, implying that at least some stable crust existed by then, but the details remain uncertain. How much crust? How stable? How widespread? The zircons whisper, but they do not explain. The magma ocean churns. The atmosphere presses down. The moon raises tides in molten stone. And somewhere, in the arithmetic of cooling and crystallization, the Earth begins its long, patient transformation toward a planet with a surface that can be walked upon, though it will be another 3 billion years before anything walks. The zircon crystals form in pockets of cooling magma, where the temperature has dropped just enough for their constituent elements, zirconium, silicon, oxygen, to bond into a stable lattice. Zircon is unusually resistant to heat, pressure, and chemical weathering. Once formed, these crystals can survive conditions that would melt or dissolve almost any other mineral. They are, in a sense, geological memory made solid, tiny time capsules that will persist for billions of years, outlasting the rocks in which they originally crystallized. The oldest known zircon, a grain called RC's January 27, 61, formed approximately 4.374 billion years ago, give or take 6 million years. It was found in a sandstone formation in the Jack Hills of Western Australia, embedded among much younger sediments. The zircon itself is only about 200 micrometers across, roughly twice the width of a human hair, but its isotopic composition tells a story. The ratios of oxygen isotopes within the crystal suggest it formed in magma that had interacted with liquid water at the surface. This implies that by 4.4 billion years ago, Earth's surface had cooled below the critical temperature of water, 374 degrees Celsius, and that stable crust capable of hosting liquid water may have already existed. But this is only one interpretation. Other scientists argue that the oxygen isotope signature could reflect recycling of water-altered materials from the solar nebula, or contamination from later geological processes. The zircon is evidence, but not proof. It is a single data point in a vast emptiness of geological time, and single data points rarely settle debates. Still, the zircons continue to form. As the magma ocean cools and differentiates, granitic melts, richer in silica than the basaltic bulk composition, begin to crystallize zircon wherever conditions allow. These crystals incorporate uranium and thorium into their structure, but exclude lead over time. The uranium decays into lead at a known rate, and by measuring the ratio of uranium to lead, geologists can calculate when the zircon formed. It is one of the most reliable clocks in geology, ticking steadily across billions of years. A crystal smaller than a grain of sand, surviving 4 billion years of heat, pressure, erosion, and burial, outlasted continents, outlasted oceans, just sitting there. Quiet. The Hadean Earth does not have continents yet, but it may have protocontinents, small. Thick rafts of buoyant crust that resist being dragged back down into the mantle. These protocontinents would be tiny by modern standards, perhaps only a few hundred kilometers across, roughly the size of Iceland or New Zealand. They would drift on the semi-molten surface, colliding occasionally, fragmenting and reforming. No geological evidence of these structures survives. If they existed, they have been completely recycled, but their existence is consistent with theoretical models of how early crust forms. The process begins with partial melting, as the upper mantle cools. Certain minerals melt preferentially, leaving behind a residue of denser material and producing a melt enriched in lighter elements. This melt rises, cools, and crystallizes into rock that is less dense than the mantle from which it came. If enough of this lighter rock accumulates in one place, it becomes buoyant, floating on the denser mantle like a raft on water. This is the beginning of continental crust. But the early crust is unstable. The mantle beneath is still hot and vigorously convecting. Plumes of hot rock rise from deep within the mantle, reaching the surface and spreading laterally, dragging pieces of crust along with them. The crust thickens in some places, thins in others, and occasionally breaks apart entirely. It is a chaotic, dynamic system. Nothing like the relatively stable plate tectonics of the modern Earth. Geologists debate whether true plate tectonics operated in the Hadean. Plate tectonics requires a specific set of conditions: a rigid lithosphere that can fracture into plates, a convecting mantle to drive their motion, and subduction zones where old crust is recycled back into the mantle. Some of these conditions may not have existed in the early Earth. The mantle was hotter, making the lithosphere thinner and less rigid. The crust may have been too buoyant to subduct efficiently. Instead of organized plates, the early Earth may have experienced a stagnant lid regime, where the crust remained relatively immobile, or a drip tectonics regime, where blobs of dense crust occasionally sank into the mantle without forming continuous subduction zones. The uncertainty is humbling. Geologists can model the thermal evolution of the early Earth, estimate mantle temperatures, calculate viscosities, and predict how rock should behave under different conditions, but without direct evidence. the models remain speculative. The Hadean is largely invisible to science, known only through inference and extrapolation. A whole eon, 500 million years, and almost no rocks survive to tell the story. Most of Earth's first act erased. What is known is that by the end of the Hadean, around 4.0 billion years ago, stable crust definitely existed. The boundary between the Hadean and the subsequent Archean eon is defined by the appearance of the first surviving rocks, ancient gneisses and greenstone belts in Canada. Greenland and Western Australia, dated to between 4.03 and 3.95 billion years. These rocks are metamorphosed, deformed, and chemically altered, but they are there. They mark the moment when Earth's crust became stable enough to persist, resilient enough to survive billions of years of subsequent geological activity. The zircons, meanwhile, continue to be discovered. Each new find adds a point to the sparse timeline of the Hadean. Some zircons show evidence of multiple growth episodes, with younger rims crystallizing around older cores, records of remelting and recrystallization, of crust being recycled and reformed. Others contain inclusions of even older minerals, tiny fragments of even earlier crust preserved within the zircon's protective lattice. One zircon, analyzed in 2014, contained an inclusion of graphite, pure carbon, whose isotopic composition suggested it might have been biological in origin. If true, this would push the origin of life back to at least 4.1 billion years ago, well into the Hadean, but the interpretation is contested. Carbon isotopes can be fractionated by non-biological processes as well, and a single inclusion in a single zircon is, once again, a fragile thread of evidence on which to hang such a profound conclusion. The zircons remain enigmatic. They are the only witnesses to the Hadean, and they speak in isotopic ratios, crystal structures, and trace element concentrations, a language that requires translation, interpretation, and always uncertainty. They remember the formation of Earth's first stable crust, but they do not explain it. They are fragments of a lost world, scattered across billions of years, waiting to be found in the sediments of a much younger Earth. The atmosphere above the molten surface is thick and hot. Water vapor circulates in vast convective cells, rising where the surface is hottest, cooling as it ascends, condensing into droplets that fall again toward the glowing rock below. But the droplets never reach the surface. The temperature gradient is too steep. At an altitude of perhaps 10 or 20 kilometers, the falling water evaporates back into vapor, absorbing heat and rising once more. The hydrological cycle operates, but it is incomplete. A cycle without oceans, without rivers, without the familiar geography of liquid water meeting solid ground. This is not because water is absent. The young Earth contains vast quantities of water, delivered during its formation by water-rich asteroids and comets from the outer solar system. Some of this water is chemically bound within minerals in the mantle. Some circulates as vapor in the atmosphere, but none of it can exist as liquid at the surface, not yet, because the surface temperature exceeds water's critical point, 374 degrees Celsius under 1 atmosphere of pressure, higher still under the thicker Hadean atmosphere. Above the critical point, water does not boil. It does not transition from liquid to gas in the familiar way. Instead, it exists in a supercritical state, a fluid that is neither liquid nor vapor but something in between, with properties that shift continuously as pressure and temperature change. Rain that falls toward the early Earth's surface passes through this supercritical transition zone, losing its identity as liquid droplets and becoming a diffuse, gas-like fluid that mingles with the hot atmosphere near the surface. The cycle continues. Heat from the molten rock warms the lower atmosphere. Water vapor rises. The upper atmosphere cools by radiating heat into space. Water condenses, droplets fall, they evaporate, the vapor rises, around and around. A hydrological cycle with no ground to complete it. No oceans to collect the rain, only heat and motion and patient, geological time. Geologists estimate that it takes tens of millions of years for the surface to cool below the critical point. The exact timeline depends on the efficiency of heat loss, the thickness of the atmosphere, the intensity of radiogenic heating, and the rate at which the mantle convects, all variables that are difficult to constrain for a planet that existed 4.5 billion years ago. Different models give different results. Some suggest the surface cooled relatively quickly, within 50 million years of the moon forming impact. Others suggest it took longer, perhaps 100 million years or more. Rain that cannot touch the ground for 50 million years, just circulating, waiting for the planet to cool enough to catch it. The cooling process is not smooth. Large impacts can temporarily reverse it. The Hadean is a time of frequent collisions. Asteroids and comets from the early solar system still litter the inner planet's orbits. And the young Earth is struck repeatedly. Each impact releases energy, heating the surface, sometimes melting large portions of the newly forming crust. A sufficiently large impact can vaporize rock, blast away part of the atmosphere, and reset the cooling process, forcing the planet to begin again. The moon-forming impact, which occurred perhaps 50 to 100 million years after the solar system's formation, is the largest of these collisions. A Mars-sized body, sometimes called Theia, strikes the proto-Earth at an oblique angle, vaporizing both impactor and a large portion of Earth's mantle. The debris from this collision coalesces into the Moon, and the Earth is left with a surface that is, once again, entirely molten, a global magma ocean, glowing white-hot, radiating heat into space. But even this catastrophic event does not stop the cooling. The magma ocean crystallizes over thousands to millions of years, depending on its depth. Minerals precipitate out of the melt in a specific sequence. First olivine and pyroxene, then plagioclase feldspar, then more evolved, silica-rich minerals. This process, called magmatic differentiation, creates the layered structure of the Earth's interior and begins the chemical separation that will eventually allow continental crust to form. As the surface cools, the water in the atmosphere cools as well. The critical point is pressure dependent, and under the thick Hadean atmosphere, water can exist as liquid at temperatures higher than 374 degrees. But the atmospheric pressure itself changes as water condenses and falls. It is a coupled system, temperature, pressure, and phase state all influencing one another. And the transition from a steam atmosphere to a planet with liquid oceans is not instantaneous but gradual, taking place over millions of years as the surface temperature drops and water begins to collect in topographic lows. The first liquid water is probably not pure. It is acidic, rich in dissolved carbon dioxide, and contains whatever other volatiles are present in the early atmosphere: sulfur dioxide, hydrogen chloride, nitrogen compounds. This water is corrosive. When it finally contacts solid rock, it begins to chemically weather the surface, dissolving minerals, altering their composition, and initiating the first sedimentary processes. But before water can pool on the surface, there must be topographic lows to contain it. The molten surface is not flat. Convection creates transient highs and lows, but these features are ephemeral, existing only as long as the underlying flow patterns persist. For liquid water to collect and remain, the crust must be solid enough to support permanent topography, mountains, valleys, basins. This requires cooling, solidification, and the formation of a rigid lithosphere, a planet waiting for its own surface to harden so that rain can finally land. Took longer than some moons have existed. The transition is recorded incompletely. In the oxygen isotopes of those ancient zircon crystals, the isotopic composition of oxygen in a mineral depends on the temperature at which it forms and the isotopic composition of the surrounding environment. Zircons that crystallized in magma with no interaction with liquid water have one isotopic signature. Zircons that formed in magma that had assimilated or interacted with water-altered rock have a different signature, lighter, enriched in oxygen-16 relative to oxygen-18. The Jack Hill zircons show this lighter signature, suggesting that by 4.4 billion years ago, liquid water had interacted with rock at Earth's surface, altering its chemistry and leaving an isotopic fingerprint. But the interpretation is not without complications. Isotopic fractionation can occur through processes other than water-rock interaction, evaporation. For instance, preferentially removes lighter isotopes, enriching the remaining water in heavy isotopes and complicating the signal. And zircons can be partially reset by later heating events, mixing old and new isotopic signatures in ways that are difficult to disentangle. The zircons suggest, but do not prove. They hint at a world with liquid water, but they do not describe it. The Hadean remains, in many ways, a mystery, a time before the rock record begins, known only through traces and inferences and the patient analysis of crystals smaller than grains of sand. The rain continues to fall, and eventually it reaches the ground. The lava that flows across the early Earth's surface is different from the lava that flows today. It is hotter, sometimes exceeding 1,600 degrees Celsius, and more fluid, with a viscosity closer to water than to the thick, pasty basalts of modern volcanoes. This is cometite, an ultramafic lava rich in magnesium and iron, named after the Komati River in South Africa, where it was first described in 1969. Comatite no longer erupts on Earth. The mantle has cooled too much. But in the Archean and late Hadean, comatite was common, perhaps even dominant, and it shaped the early crust in ways that modern lavas cannot. Comatite flows are fast. Where basaltic lava might advance at a few meters per hour, comatite can flow at speeds of tens of kilometers per hour, racing across the landscape like a river of molten stone. The high temperature keeps the lava extremely fluid, and the low viscosity allows it to travel great distances from its source. Some comatite flows are hundreds of kilometers long, spreading out in broad sheets that cover vast areas before finally cooling and solidifying. The surfaces of these flows are distinctive. As comatite cools, it develops a texture called spinifex, named after a type of spiky Australian grass. Spinifex texture forms when olivine crystals grow rapidly from the surface of the flow downward into the still liquid interior, creating long, blade-like crystals that radiate in clusters. The result is a rock that looks almost botanical, sharp, green, and geometric, like frozen vegetation made of stone. It is one of the most striking textures in geology, and it is found only in very old rocks, a signature of a hotter Earth. Lava that flows like water, crystals that grow like grass. Just ordinary early Earth things. Impossible now. The comatite flows carve channels into the semi-solid crust beneath them. The heat of the lava melts the substrate, and the flow thermally erodes its own pathway, deepening and widening the channel as it advances. These channels can be tens of meters deep, with steep walls and flat floors, and they preserve a record of the flow's passage, a snapshot of dynamic processes frozen in stone. When the flow finally stops and solidifies, the channel remains, sometimes filled with later flows, sometimes empty, always distinctive. Geologists study these ancient channels to understand how comatite behaved. The depth of thermal erosion indicates the flow's temperature and velocity. The width of the channel constrains the volume of lava. The geometry of the deposits reveals whether the flow was turbulent or laminar, fast or slow, continuous or pulsed. Each cometite flow is a record of a volcanic event that occurred billions of years ago, and by piecing together these records, scientists can reconstruct the conditions under which the early crust formed. Cometite also plays a role in the formation of valuable mineral deposits. Because it is so hot and fluid, cometite can dissolve and transport metals, nickel, copper, platinum group elements that are normally locked in solid rock. When the cometite cools, these metals precipitate out, concentrating in specific zones within the flow. Some of the world's richest nickel deposits are found in Archean cometite flows, mined today for the metals they concentrated billions of years ago. But in the Hadean and early Archean, there is no mining, no economy, no value attached to these concentrations. The cometite simply flows, cools, and solidifies, building up layers of ultramafic rock that will eventually be metamorphosed, buried, and incorporated into the stable continental crust. The processes are purely physical and chemical: heat, gravity, crystallization, erosion. The planet is arranging itself, sorting its materials by density and composition, building the foundation for everything that will come later. The source of cometite is the mantle, specifically the upper mantle, which in the Hadean is perhaps 200 degrees hotter than it is today. This hotter mantle melts more easily and produces larger volumes of melt. When a mantle plume, a column of hot rock rising from deep within the Earth, reaches the base of the crust, it melts partially, producing cometite magma that ascends through fractures and erupts at the surface. These eruptions are not explosive. Cometite has very low volatile content, little water, little carbon dioxide, and so it erupts effusively, pouring out of fissures and spreading across the surface in broad flows. There are no volcanic cones, no ash clouds, no pyroclastic surges, just lava flowing downhill, following topography, pooling in depressions, and eventually solidifying into green, spinifex-textured stone. Took longer for the mantle to cool than for humans to evolve from shrews. Still cooling, just slower now. The cometite flows interact with water where water is present. When hot lava meets liquid water, the result is a phreatomagmatic eruption, an explosion driven by the rapid expansion of steam. The water flashes to vapor, fragmenting the lava into tiny particles that are blasted into the air and then settle as volcanic ash. These deposits, called hyaloclastites, are found interbedded with cometite flows in some Archean greenstone belts, indicating that liquid water was indeed present at the surface during at least some eruptions. But the presence of water is sporadic and localized. Much of the early Earth's surface remains too hot for standing water, and cometite erupts onto dry land, or onto temporarily solidified crust, or into shallow magma chambers, where it interacts with other melts and crystallizes underground. The geological record is fragmentary. Some cometite flows are preserved in their original form, others are metamorphosed beyond recognition. Still others are destroyed entirely, recycled back into the mantle through subduction or delamination, leaving no trace. What remains is enough to tell a story, but not enough to fill in all the details. The cometite flows speak of a hot mantle, a dynamic surface, and volcanic processes unlike anything operating on Earth today. They are relics of a vanished world, green stones in ancient cratons, waiting to be found and interpreted and wondered at. The flows continue. The surface builds up, layer by layer, flow by flow, and slowly, incrementally, the foundations of the first stable crust take shape. Inside the planet, beneath the flows and the forming crust, a quieter process unfolds. Density sorts the interior, heavy elements sink, light elements rise. This is differentiation. the separation of a chemically mixed body into layers of distinct composition, and it is one of the most fundamental processes in planetary evolution. Without differentiation, there would be no core, no mantle, no crust. Earth would remain a homogeneous ball of mixed materials, undifferentiated and geologically inert. The process begins during accretion. As planetesimals collide and merge, their kinetic energy converts to heat. The proto-Earth grows hotter with each impact, and eventually it becomes hot enough for iron to melt. Liquid iron, being denser than the surrounding silicate rock, begins to sink toward the center of the planet. This is the iron catastrophe. Catastrophic not in the sense of disaster, but in the sense of sudden, profound change. The sinking iron releases gravitational potential energy, which converts to heat, which melts more rock, which allows more iron to sink. It is a runaway process, completed in perhaps 10 to 100 million years. By the time the Hadean begins, the core is largely formed. The Earth has a liquid outer core of molten iron-nickel alloy, perhaps already beginning to crystallize an inner core of solid iron at the very center. The core's formation has stripped most of the iron from the mantle, leaving behind a silicate mantle enriched in lighter elements: magnesium, silicon, oxygen, aluminum, calcium. This mantle is still hot, still partially molten in places, and it continues to convect vigorously, driven by heat escaping from the core below and by radiogenic decay within the mantle itself. Differentiation does not stop at the core mantle boundary. The mantle itself differentiates. As it cools and crystallizes, denser minerals sink and lighter minerals rise. The process is complex, involving partial melting, fractional crystallization, and chemical exchange between solid and liquid phases. Over time, the mantle develops a layered structure, an upper mantle of relatively light, easily melted rock, and a lower mantle of denser, more refractory material. This layering influences how the mantle convects, which in turn influences how heat escapes from the planet, which in turn influences the formation and evolution of the crust. Spent 100 million years just settling into layers, not even building anything yet, just organizing. The crust is the final product of differentiation, the lightest, most incompatible elements, concentrated at the surface. Incompatible is a technical term in geochemistry. It refers to elements that do not fit easily into the crystal structures of common mantle minerals. When the mantle partially melts, these incompatible elements preferentially enter the melt, leaving behind a solid residue depleted in those elements. The melt rises, carrying the incompatible elements with it, and when it crystallizes at the surface, it forms rock that is enriched in these elements relative to the mantle. The incompatible elements include many of the constituents of continental crust: silicon, aluminum, potassium, sodium, as well as trace elements like uranium, thorium, and the rare earth elements. These elements are crucial for understanding crustal formation because their concentrations and ratios provide clues about the melting processes that produce the crust. A rock rich in incompatible elements has likely been through multiple stages of melting and crystallization, each stage concentrating the incompatible elements further. Continental crust, with its high silica content and enrichment in incompatible elements, is the product of extensive differentiation, the mantle's lightest, most processed fraction. But producing continental crust is not straightforward. The mantle does not directly produce granite. Partial melting of the mantle produces basalt, the dark, dense rock that makes up oceanic crust. To get granite, basalt must be melted again, a process called remelting or anatexis. This requires water, which lowers the melting point of rock, and it requires specific tectonic settings, subduction zones, continental collision zones, places where water-saturated crust is buried and heated until it melts. Whether these settings existed in the Hadean is uncertain. Some models suggest that the early Earth produced felsic crust, rock with a composition similar to granite, through a different mechanism. In a hotter mantle, it is possible for partial melting to directly produce more silica-rich melts, especially if the melting occurs at shallow depths or in the presence of water. These melts would crystallize into rocks intermediate in composition between basalt and granite, andesites and dacites, which could then be further processed into true continental crust through erosion, sedimentation, and metamorphism. Other models invoke a stagnant lid regime, where thick, buoyant crust accumulates at the surface and is repeatedly remelted from below by mantle plumes, each episode of melting producing progressively more evolved, silica-rich rock. In this scenario, the crust builds up over time through vertical processes rather than through plate tectonics. The uncertainty is profound. Geologists do not know which mechanism dominated in the Hadean. Perhaps multiple mechanisms operated simultaneously, producing crust in different ways in different locations. Perhaps the processes changed over time, as the mantle cooled and the planet's interior evolved. The rock record is silent, and so scientists rely on models, experiments, and comparisons with other planets to infer what might have happened on the early Earth. A whole category of rock, granite, the foundation of continents, and no one is entirely sure how the first batches formed. Maybe subduction, maybe plumes, maybe both, maybe neither. What is certain is that by the end of the Hadean, felsic crust existed. The Jack Hill's zircons, with their granitic chemistry, prove that. And felsic crust, once formed, is difficult to destroy. It is less dense than basalt, and much less dense than the mantle, so it resists subduction. It floats. It accumulates. It becomes the nuclei of the first protocontinents, the seeds from which modern continents will eventually grow. Differentiation continues. The planet sorts itself, heavy to the center, light to the surface, and at the surface, the lightest fraction of all begins to coalesce into something that will, in time, be called land. The impacts do not stop. The Hadean is a shooting gallery, the inner solar system still cluttered with debris from the accretion process, asteroids and comets in eccentric orbits, planetesimals that escaped incorporation into the planets and now wander chaotically through the gravitational fields of the Sun and the newly formed worlds. The young Earth is struck frequently, every few thousand years, a large impact, every few 100,000 years, a massive one, every few tens of millions of years, a catastrophic collision capable of vaporizing rock and reshaping the planet's surface. The craters these impacts create are enormous. An asteroid 10 kilometers across, striking at 20 kilometers per second, excavates a crater perhaps 200 kilometers in diameter. The energy released is equivalent to billions of nuclear weapons. Rock vaporizes. The shock wave propagates through the crust. Earthquakes ripple outward. Ejecta is blasted into ballistic trajectories, raining back down across thousands of kilometers. The impact site glows white-hot for hours, radiating heat into the atmosphere. And then, slowly, over days and weeks, it begins to cool. But the crater does not persist. On a modern, solid planet, an impact crater can remain recognizable for billions of years. Witness the ancient craters on the Moon, sharp-rimmed and pristine, preserved in the lunar highlands since the late heavy bombardment. But on the semi-molten Hadean Earth, craters are ephemeral. The surface is not rigid, the crust is thin, underlain by partially molten rock, and still hot enough to flow under stress. The crater begins to fill almost immediately. Magma from below wells up into the depression. The crater walls slump inward, their steep slopes too unstable to support themselves. Within centuries, the crater is partially filled. Within millennia, it is indistinguishable from the surrounding terrain. The impact has melted and fractured the crust. But the crust heals itself, not through any active repair mechanism, but simply through the inexorable flow of hot rock seeking equilibrium. The surface is self-annealing, a crater 200 kilometers wide, erased in a few thousand years. On the Moon. That same crater would still be there today, sharp as the day it formed. Just different planets, different rules. The impactors themselves contribute to the planet. Each asteroid delivers not only kinetic energy, but also mass, rock, metal, and volatiles. Some of Earth's water may have arrived this way, carried by comets and water-rich asteroids from the outer solar system. Some of the planet's atmosphere may have been augmented by outgassing from impacts, the volatile-rich impactors releasing their trapped gases upon collision. Each impact is, in a sense, a delivery, bringing materials from elsewhere in the solar system to the growing Earth. But the delivery comes at a cost. The energy of the impact heats the surface, sometimes remelting crust that had only recently solidified. Large impacts can strip away part of the atmosphere, blasting gas into space through the sheer force of the collision. Very large impacts, like the moon-forming impact, can reset the planet's thermal evolution entirely, returning the surface to a molten state and forcing the cooling process to begin again from scratch. Geologists refer to this as impact frustration, the idea that the formation of stable crust is repeatedly delayed by large impacts that destroy whatever crust has managed to form. In this view, the Hadean is a time of two competing processes, cooling and solidification on one hand, and impact-driven remelting on the other. Only when the impact rate declines, as the solar system clears out its debris, can the crust finally stabilize and persist. The late heavy bombardment, which occurs around 3.9 billion years ago, near the end of the Hadean, is the last major episode of intense cratering in the inner solar system. Its cause is debated. Perhaps the migration of the giant planets destabilized the asteroid belt, flinging a shower of impactors toward the inner planets, but its effects are clear. The Moon's surface is saturated with craters from this period. Mars shows evidence of major impacts. Mercury is heavily cratered. And Earth, though the evidence has been erased by subsequent geological activity, must have been struck as well, perhaps dozens of times by impactors large enough to vaporize oceans and melt the crust. But by this time, the crust is more stable. The mantle has cooled. The surface is solid enough to resist complete remelting. The impacts create large craters, some hundreds of kilometers across, some perhaps even larger. But these craters no longer vanish within millennia. They persist for millions of years, slowly eroding, slowly filling with sediment and lava, but recognizable as impact structures. The planet has transitioned from a surface that heals itself to a surface that records its history. Took 400 million years to build a surface that could remember its own scars. Before that, every wound closed itself, just flowed shut. The impactors themselves are diverse. Some are stony asteroids, composed mainly of silicate minerals, similar in composition to the Earth's mantle. Others are iron-nickel meteorites, fragments of the cores of shattered planetesimals, dense and metallic. Still others are carbonaceous chondrites, primitive asteroids rich in organic compounds and water. Little change since the solar system's formation. Each type of impactor leaves a different chemical signature in the rocks it melts and vaporizes. And by studying these signatures, where they can be found, geologists can reconstruct something of the population of impactors that bombarded the early Earth, but such signatures are rare. Most Hadean impact structures are gone, obliterated by erosion, subduction, and metamorphism. What remains are a few anomalous chemical signatures in very old rocks, layers enriched in platinum group elements, or shocked minerals that only form under the extreme pressures of an impact, or spherules of melted rock that cooled rapidly while airborne and then settle to the surface as tiny glass beads. These are the traces of ancient impacts, faint and scattered, preserved by chance in rocks that have themselves survived 4 billion years of geological upheaval. The bombardment tapers off, the solar system empties, the impacts become less frequent, and the Earth's surface, battered but intact, begins to solidify in earnest. The protocontinents are small. They do not span oceans or host mountain ranges or support ecosystems. They are fragments, thick patches of buoyant crust, perhaps 100 kilometers across, floating on the denser mantle like ice floes on a sea. They are not yet continents in any meaningful sense, but they are stable. They resist being dragged back down into the mantle. They persist. The process by which these protocontinents form is called crustal thickening. In regions where mantle plumes rise or where multiple volcanic centers are active, magma accumulates at the surface faster than it can be recycled back into the mantle. The crust grows thicker, and as it thickens, its lower portions are buried deeper, subjected to higher pressures and temperatures, and eventually begin to melt. This melting produces a more evolved magma, richer in silica, lighter, more buoyant, which rises and intrudes into the overlying crust, thickening it further. It is a self-reinforcing process. Thick crust produces felsic magma, and felsic magma makes the crust even thicker and more buoyant. The protocontinents drift. They are not anchored. The mantle beneath them is convecting, and the convection currents drag the surface crust along, moving the protocontinents like rafts on a slow current. They move at speeds of perhaps a few centimeters per year, plate tectonic speeds, though whether true plate tectonics operates in the Hadean is still debated. The protocontinents collide occasionally, merging into larger fragments, or they are pulled apart, fragmenting into smaller pieces. Nothing is permanent. Everything is in motion. Continents the size of cities, drifting, colliding, melting, reforming, just trying to figure out how to stay afloat. Geologists have a term for this process: continental nucleation. It is the idea that modern continents began as small nuclei, stable, buoyant fragments of thick crust that gradually accumulated more material over billions of years, growing by magmatic addition, sedimentary accretion, and tectonic collision. The protocontinents of the Hadean and early Archean are these nuclei, the seeds from which the continents will eventually grow. But the protocontinents are fragile. They can be destroyed. If a protocontinent is overridden by a mantle plume, the intense heat can melt it from below, reincorporating it into the mantle. If it drifts over a downwelling current, a place where cool, dense mantle rock is sinking, it can be dragged down with the flow, subducted and destroyed. The balance between creation and destruction is delicate, and many protocontinents likely form and disappear without leaving any trace in the geological record. What allows a protocontinent to survive is buoyancy. Continental crust is less dense than oceanic crust, and much less dense than the mantle. Typical continental crust has a density of about 2.7 grams per cubic centimeter, compared to 3.0 for oceanic crust and 3.3 for the upper mantle. This difference may seem small, but it is enough. A thick raft of continental crust, once formed, is difficult to subduct. It floats. It resists being pulled down into the mantle, even when the mantle is vigorously convecting. The composition of these protocontinents is inferred from the oldest surviving rocks, the Acasta gneiss in Canada, dated to 4.03 billion years, and the Nuvuagittuq greenstone belt, also in Canada, which may be even older. These rocks are metamorphosed, their original textures and structures largely erased by billions of years of heat and pressure. But their chemistry remains. They are tonalite trondhjemite granodiorite suites, TTG for short, a family of felsic igneous rocks that are common in Archean terrains and are thought to represent the composition of early continental crust. TTG rocks are distinguished from modern granites by their chemistry. They are richer in sodium than potassium, and they have distinctive trace element patterns that suggest they formed by melting of hydrated basalt at high pressure, conditions consistent with subduction or with melting at the base of thick oceanic crust. Whether this implies that plate tectonics operated in the Hadean and early Archean, or whether TTGs can form through alternative mechanisms, remains a subject of active debate. Rocks with chemistry this specific, telling a story about pressure and water and melting, but not quite agreeing on where or how they formed, geology in a nutshell. The protocontinents are not barren. Once the surface cools enough for liquid water to exist, erosion begins. Rain falls on the protocontinental highlands, chemically weathering the rock, dissolving minerals, and carrying the dissolved material downslope. The water collects in topographic lows, forming the first rivers, the first lakes, perhaps even the first shallow seas. Sediment accumulates, sand, silt, clay, the products of erosion, and these sediments are the first sedimentary rocks, the first materials on Earth's surface that were not directly formed by cooling magma. But sedimentary rocks from the Hadean do not survive. They are too fragile, too easily metamorphosed, too readily subducted. The oldest known sedimentary rocks date to the early Archean, around 3.8 billion years ago, and even these are heavily altered. To find evidence of Hadean sedimentation, geologists must look for indirect signs, detrital zircons that have been eroded from igneous rocks, transported by water, and deposited in younger sediments. These zircons prove that erosion and sedimentation were occurring, but they do not describe the landscapes being eroded or the environments in which the sediments were deposited. The protocontinents grow slowly. Magmatism adds new rock from below. Volcanic eruptions pile lava and ash on the surface. Sediments accumulate in basins, and occasionally, protocontinents collide, welding together into larger landmasses. These collisions are the earliest form of mountain building, orogenesis, though the mountains formed are probably low and broad, nothing like the steep, high ranges of the modern Earth. The crust is still hot, still weak, and tall mountains would simply collapse under their own weight. The first cratons, the stable cores of modern continents, begin to take shape. A craton is a piece of continental crust that has been stable for billions of years, undeformed by tectonic activity, resistant to erosion and subduction, the oldest cratons. Like the Kapval Craton in South Africa and the Pilbara Craton in Western Australia, preserve rocks from the early Archean and possibly the late Hadean. They are the survivors, the fragments of protocontinents that managed to persist through 4 billion years of geological tumult. But in the Hadean, these cratons are not yet stable. They are still forming, still evolving, still vulnerable to destruction. They are experiments in continental crust, some of which will succeed and become the ancient cores of modern continents, and some of which will fail and disappear back into the mantle. Leaving no trace, the protocontinents drift, the surface cools, the crust thickens, and slowly, patch by patch, the first permanent landmasses take shape, small, scattered, and provisional, but unmistakably there, beneath the forming crust. The mantle moves. It rises in plumes where it is hot and buoyant. It sinks in sheets where it is cool and dense. This is convection, the transport of heat by the motion of a fluid, and it is the engine that drives almost all geological activity. Without mantle convection, there would be no volcanism, no plate tectonics, no mountain building, no earthquakes. The Earth would be geologically dead, its interior heat trapped and unable to escape. But the nature of mantle convection in the Hadean is uncertain. On the modern Earth, Convection is organized into a pattern of upwelling ridges and downwelling subduction zones, with rigid plates moving across the surface in response to the flow beneath. This is plate tectonics, and it is an efficient system for transporting heat from the interior to the surface. But plate tectonics requires specific conditions: a rigid lithosphere that can fracture into plates, a weak asthenosphere that allows the plates to move, and a mechanism for recycling old lithosphere back into the mantle through subduction. In the Hadean, these conditions may not have been met. The mantle is hotter, which makes the lithosphere thinner and weaker. The crust is more buoyant, which makes subduction more difficult, and the convection patterns may be different, dominated by vertical plumes and downwellings rather than by horizontal plate motion. Some geologists describe this as a stagnant lid regime, where the surface crust is largely immobile, broken only occasionally by volcanic eruptions or by the sinking of dense crustal blobs. Others propose a drip tectonics model, where thick, dense portions of the crust occasionally become unstable and sink into the mantle in discrete events, rather than being continuously recycled through subduction zones. In this model, the surface is not entirely stagnant, but neither does it exhibit the organized, linear subduction zones of modern plate tectonics. Instead, recycling occurs in isolated locations, driven by gravitational instability rather than by large-scale convection. A whole tectonic system, but maybe not plate tectonics, maybe just blobs sinking, maybe just plumes rising. No one knows for sure. The evidence for or against Hadean plate tectonics is sparse. True plate tectonics leaves distinctive geological signatures: linear belts of deformed rock, paired metamorphic belts with contrasting pressure-temperature conditions, ophiolites, sections of oceanic crust thrust onto continents, and blue schists, metamorphic rocks that form under the high pressure, low temperature conditions of subduction zones. None of these features are definitively known from Hadean rocks, but that may simply reflect the poor preservation of the Hadean rock record rather than the absence of plate tectonics. Some scientists point to the Jack Hill zircons as evidence for subduction. The zircons' chemistry suggests they formed in magmas similar to those produced at modern subduction zones, melting of hydrated, subducted oceanic crust. If this interpretation is correct, then some form of subduction, and therefore some form of plate tectonics, was operating by 4.4 billion years ago. But the interpretation is contested. Zircon chemistry is complex, and similar signatures can be produced by other processes, melting at the base of thick crust, for instance, or contamination of mantle-derived magmas by crustal material. Other scientists argue that true plate tectonics could not have begun until the mantle cooled sufficiently for the lithosphere to become rigid. They point to geodynamic models showing that a hotter mantle produces a weaker, more deformable lithosphere that cannot sustain the large stresses required for subduction. In these models, plate tectonics is a relatively recent phenomenon, beginning perhaps in the Neoproterozoic, only 1 billion years ago, or in the Archean, around 3 billion years ago. Before that, the planet operated under a different tectonic regime, one without plates, without continuous subduction, without the efficient heat transport that characterizes the modern Earth. The debate is unresolved. Geologists examine the same rocks, the same zircons, the same chemical data, and reach different conclusions. This is not a failure of science, but a reflection of the difficulty of the problem. The Hadean is a time for which the evidence is fragmentary, and the boundary conditions are poorly constrained. Multiple models can fit the available data, and distinguishing between them requires more information than currently exists. What is clear is that the mantle is convecting. Heat is escaping from the interior. The surface is volcanically active. Crust is forming, and at least some of it is being recycled back into the mantle. Whether through organized subduction or through less systematic processes, the planet is dynamic, not static. It is evolving. Spent decades debating whether there were moving plates or sinking blobs. Both camps had good arguments. Still debating. If subduction is occurring, it is probably different from modern subduction. The subducting slabs may be hotter, weaker, more likely to break apart or to melt before they reach great depths. The volcanic arcs above the subduction zones may be more mafic, less evolved, producing basalt and comatite rather than andesite and rhyolite, and the subduction zones themselves may be shorter-lived, more mobile, less linearly organized than the long, stable subduction zones that ring the Pacific Ocean today. Alternatively, if drip tectonics dominates, the crust may be recycled in pulses rather than continuously. A thick pile of dense crust accumulates over millions of years. It becomes gravitationally unstable. Suddenly, on geological timescales, it founders and sinks, carrying surface material deep into the mantle in a single event. The surface subsides, magma wells up to fill the void, and the process begins again. Either way, the mantle is hungry. It consumes crust. It mixes surface materials back into its interior, and in doing so, it homogenizes the chemical signatures of early differentiation, erasing much of the evidence that might otherwise reveal how the Hadean Earth operated. The convection continues. The plumes rise, the slabs or blobs or whatever they are descend, and the planet, still hot, still violently active, churns itself toward a cooler, more stable future. The moon is close, absurdly close by modern standards. It hangs enormous in the sky, perhaps 15 or 20 times larger in apparent diameter than the moon visible from Earth today. At a distance of only 20,000 kilometers, roughly 1/15 its current orbital radius, the moon's gravitational influence on the young Earth is profound. Tides are not gentle, they are extreme. On the modern Earth, tides raise the ocean surface by a meter or two. The solid Earth itself also deforms tidally, but only by a few tens of centimeters, barely noticeable without sensitive instruments. But on the Hadean Earth, with the moon so close and the surface so hot and weak, tidal deformation is dramatic. The solid surface itself bulges outward toward the moon and away from it on the opposite side, creating tidal bulges perhaps tens or even hundreds of meters high in the semi-molten crust. These tidal bulges sweep around the planet as Earth rotates beneath the moon. The Hadean day is short, only 5 or 6 hours long, and so the tidal bulges race across the surface, flexing the crust in a rapid, rhythmic cycle. The flexing generates heat through friction. The crust deforms, and the deformation dissipates energy, warming the rock and slowing Earth's rotation. This is tidal dissipation, and it is a major source of heat in the early Earth, comparable in magnitude to radiogenic heating. The tidal flexing also affects the moon. The gravitational interaction transfers angular momentum from Earth's rotation to the moon's orbit, causing the moon to slowly spiral outward. The process is gradual. The moon recedes by only a few centimeters per year, even in the early system, but over billions of years, the effect is substantial. The moon that orbits at 20,000 kilometers in the Hadean will eventually drift out to 380,000 kilometers, its current distance, and the tidal forces that once flexed the Hadean crust will diminish to the gentle, almost imperceptible deformations observable today. A moon so close it raised tides in solid rock took 4 billion years to drift out to a respectable distance, just slowly backing away. The tides in the molten surface are not like ocean tides. There is no water yet, or if there is water, it is scattered in isolated pools and proto-oceans, not yet connected into a global ocean. The tides are tides of magma, or of semi-solid, partially molten crust. The material flows in response to the moon's gravitational pull, bulging outward, and then relaxes as the moon moves on. The flow is slow, Viscous, but persistent, these magmatic tides may play a role in crustal formation. The flexing generates fractures and zones of weakness where magma can ascend more easily. Volcanic activity may be concentrated in regions where tidal stresses are highest, creating linear volcanic chains or elongated zones of crustal thickening. The tidal bulges themselves create topography, and this topography influences where water collects when the surface finally cools enough for liquid water to persist. But the details are speculative. No one has observed tides in a magma ocean. No analog exists on any other body in the solar system today. The best geologists can do is model the process, using equations that describe the behavior of viscoelastic materials under periodic stress, and then compare the predictions to the sparse evidence available from ancient rocks. The models are suggestive, but not definitive. The Moon's proximity also affects Earth's rotation in another way. The tidal friction not only slows the rotation, but also stabilizes it. A planet's rotation axis tends to wobble over time, driven by gravitational perturbations from the Sun and other planets. This wobble, called axial precession, can cause large changes in climate by altering the distribution of sunlight on the planet's surface. But a large, close moon damps these wobbles, stabilizing the rotation axis and keeping the climate more constant. Earth's moon has been doing this throughout its history, and may have played a crucial role in making Earth a stable, habitable planet. But in the Hadean, habitability is not yet a concern. There is no life, the surface is too hot, the environment too hostile. The moon's stabilizing influence is purely academic, affecting a planet that is not yet ready to support biology. Still, the stabilization occurs, setting the stage for everything that will come later. The moon also reflects sunlight back to Earth, providing illumination during the long Hadean nights. But with the day only 5 or 6 hours long, the nights are short as well, 2 or 3 hours of darkness, interrupted by the enormous moon rising and setting rapidly across the sky. The reflected sunlight is intense, perhaps bright enough to cast sharp shadows even at midnight. The Hadean Earth is never truly dark. Day 5 hours long, moon 15 times bigger in the sky, night almost as bright as day. Just normal early Earth things. As the moon recedes, the tides weaken, the day lengthens, the tidal flexing of the crust diminishes. By the end of the Hadean, the moon is perhaps 50 or 60,000 kilometers away, still much closer than today, but far enough that tidal heating is no longer a dominant factor in the planet's thermal budget. The crust solidifies more completely, the surface stabilizes, the moon continues its slow outward drift, and the Earth, no longer needed and flexed by such extreme tidal forces, begins to cool more efficiently. The tidal history is recorded. Faintly, in the layering of some ancient sedimentary rocks, tidal rhythmites, thin layers of sediment deposited by tidal currents, show patterns that reflect the length of the day and the month at the time they were deposited. The oldest known tidal rhythmites date to the late Archean, around 5 billion years ago, and they indicate that at that time, the day was about 18 hours long and the moon was perhaps half its current distance. Extrapolating backward, this is consistent with a much closer moon and a much shorter day in the Hadean. But no Hadean rhythmites survive. The record is lost. The tides of the earliest Earth are known only through inference, through models, through the backward extrapolation of later data. The moon was there. The tides were extreme, and the planet was shaped, in ways both obvious and subtle. By the presence of its enormous companion in the sky, water finds its first pools. The surface temperature has dropped below the critical point. Steam condenses into liquid droplets that fall and do not immediately evaporate. The droplets collect in topographic lows, depressions in the newly solidified crust. basins formed by volcanic subsidence, impact craters that have not yet healed themselves. The first pools are small, perhaps only a few kilometers across, and they are ephemeral. Volcanic activity evaporates them. Erosion fills them with sediment. They freeze and thaw as the young planet's climate oscillates wildly, but they persist long enough to begin the work of weathering, of chemical alteration, of transforming volcanic rock into something new. The water is not pure. It is acidic, saturated with dissolved carbon dioxide from the thick atmosphere. The pH is low, perhaps 3 or 4, comparable to vinegar or acid rain. This acidic water is highly reactive. It dissolves minerals from the rock, leaching out sodium, potassium, calcium, magnesium, and silicon. The dissolved ions alter the water's chemistry, and as the water evaporates or cools, minerals precipitate out, salts, carbonates, clays. The cycle of dissolution and precipitation is the beginning of sedimentary geochemistry, the chemical conversation between water and rock that will shape the planet's surface for the next 4 billion years. The first oceans, if they can be called oceans, are shallow and scattered. There is no global ocean basin yet. The crust has not differentiated into distinct oceanic and continental regions. Instead, there are patches of thicker, more buoyant crust, the protocontinents, and patches of thinner, denser crust, and water collects wherever the topography allows. These early seas are probably warm, perhaps 50 or 70 degrees Celsius, heated from below by the still hot crust and from above by the greenhouse atmosphere. Ocean basins that were really just puddles in low spots. Warm, acidic puddles on a planet with no beaches. Took millions of years to connect. The volume of water is uncertain. Estimates range from roughly the same as the modern ocean, about 1.4 billion cubic kilometers, to significantly less, perhaps only a tenth or a quarter of that amount. The uncertainty arises because no one knows how much water was delivered during accretion, how much was outgassed from the mantle during the Hadean, and how much was lost to space through atmospheric escape. Hydrogen, being light, can escape from the top of the atmosphere if it gains enough energy. Water vapor in the upper atmosphere is broken apart by ultraviolet radiation from the sun, and the resulting hydrogen atoms can then be lost to space, leaving oxygen behind. This process, called hydrodynamic escape, may have been significant on the early Earth, especially during periods when the surface was hot and the atmosphere was steam-rich. But some water remains, enough to begin the hydrological cycle, enough to fill basins and pools, enough to erode rock, transport sediment, and create the first sedimentary deposits. The presence of liquid water on the Hadean Earth is strongly suggested by the oxygen isotopes in the Jack Hill's zircons, and by the fact that by the early Archean, undisputed sedimentary rocks exist, including banded iron formations that require an ocean to form. The transition from a steam atmosphere to an atmosphere with liquid oceans is gradual and probably non-linear. As water condenses and rains down, the atmospheric pressure drops, which raises the boiling point of water, which allows more water to condense. It is a positive feedback loop. Condensation begets more condensation, and it may accelerate once it begins. Some models suggest that the transition could occur relatively rapidly, within a few million years, once the surface temperature drops below a critical threshold. During this transition, the planet experiences a water deluge, a period of intense, continuous rainfall as the atmosphere dumps its water content onto the surface. The rainfall is heavy, perhaps meters per year, and it continues for thousands or tens of thousands of years until the atmosphere is largely cleared of water vapor and a stable ocean exists at the surface. The deluge fills every basin, every depression, every low point in the topography, creating a planet-wide network of interconnected seas and lakes. But the ocean is not yet global. The topography is too irregular, the protocontinents too numerous and scattered. Water collects in the low areas, but there are also high areas, volcanic plateaus, thickened crustal rafts that remain above sea level. The early Earth has land and water, but they are intermixed, patchy, not yet organized into the distinct continents and ocean basins of the modern world, reigned for 10,000 years. Not continuously, but close, just emptying an atmosphere's worth of steam onto a cooling surface, casual. The presence of liquid water initiates true erosion. Rain falls on the exposed rock. It dissolves minerals. It seeps into fractures, expanding and contracting with temperature changes, mechanically breaking the rock apart. The broken fragments are washed down slope by running water, transported to lower elevations, and deposited as sediment. This is the beginning of the sedimentary cycle: erosion, transport, deposition, and it is fundamentally dependent on liquid water. The first rivers are small and ephemeral, flowing only during and immediately after rainstorms, drying up in between. But as the climate stabilizes and the rainfall becomes more regular, the rivers become more permanent. They carve valleys into the volcanic rock, creating drainage networks that channel water from the highlands to the lowlands. The rivers carry sediment, and where they enter standing water, a lake or a proto-ocean, they deposit that sediment, building deltas and submarine fans, the first recognizable sedimentary landforms. The sediment itself is distinctive, because the crust is almost entirely volcanic in origin. The sediment is composed of weathered basalt and comatite, rich in iron, magnesium, and calcium, poor in quartz and other resistant minerals. The clay minerals that form from the weathering of these rocks are different from modern clays, smectites and chlorites rather than kaolinite, reflecting the different composition of the source rock and the different chemistry of the water. And the sediment does not travel far. The relief is low, the rivers short, and much of the sediment is deposited close to its source. The sedimentary record of the early Archean, and by inference, the late Hadean, consists largely of locally derived volcanic debris, with little input of material from distant sources. The planet does not yet have the long, integrated river systems that characterize modern continents, systems that can transport sediment thousands of kilometers from mountains to ocean basins. The water continues to accumulate. The oceans deepen. The land begins to emerge as distinct from the sea, and the chemical interaction between water and rock begins to transform both, setting the stage for the next great change in Earth's history, the chemical evolution of the atmosphere and ocean, and, eventually, the origin of life. Granite emerges as a quiet revolution. Not in the dramatic sense. There are no explosions, no sudden appearances, but in the geological sense, as a transformation that changes everything that follows. Granite and its close relatives, granodiorite, tonalite, trondhjemite, are the rocks that make up the bulk of continental crust. They are light in color, rich in silica and aluminum. And crucially, they are buoyant. Granite floats on the denser basaltic and ultramafic rocks beneath it. And this buoyancy is what allows continents to rise above sea level and persist for billions of years. But granite does not form directly from the mantle. The mantle, when it partially melts, produces basalt, dark, dense, iron-rich rock. To get granite requires additional steps, additional processing. The basalt must be melted again, often in the presence of water, which lowers the melting point and allows the rock to partially melt at temperatures far below the melting point of dry rock. This second melting separates the light elements from the heavy ones, concentrating silicon, aluminum, sodium, and potassium in the melt, and leaving behind a residue rich in iron and magnesium. The result is a felsic magma, felsic from feldspar and silica, that is lighter, more viscous, and more evolved than the mafic magma from which it derived. This felsic magma rises through the crust, intrudes into overlying rock, and slowly cools, crystallizing into granite. The process takes millions of years. The granite bodies, called plutons or batholiths, are enormous, sometimes hundreds of kilometers across, and their formation represents the concentration of an entire region's worth of incompatible elements into a single mass of buoyant rock. Granite. The result of melting rock, cooling it, then melting it again. Twice baked stone. Took longer than some species persist. In the Hadean, the mechanism of granite formation is debated. On the modern Earth, granite forms primarily in subduction zones, where water-rich oceanic crust is dragged down into the mantle, partially melts, and produces felsic magmas that rise into the overlying volcanic arc. This is the dominant mode of continental growth today, and it requires plate tectonics. But if plate tectonics did not operate in the Hadean, or operated differently, then granite must have formed by another mechanism. One possibility is melting at the base of thick oceanic crust. If volcanic activity piles up enough basalt in one place, the lower portion of the pile is buried deep enough and becomes hot enough to melt, producing felsic magma without requiring subduction. This mechanism, called basaltic underplating, can produce rocks with a composition similar to granite, and it does not require plate tectonics. Another possibility is direct melting of hydrated comatite. Comatite, being ultramafic, has a very low silica content, but if it is hydrated, if water is incorporated into its mineral structure and then melted, the resulting magma can be surprisingly felsic, richer in silica than might be expected. This process has been demonstrated in laboratory experiments, and it may have been important in the Hadean when comatite was common. A third possibility is remelting of existing felsic crust. Once some granite has formed, it can be remelted by later volcanic activity or by burial and heating, producing yet more granite. This is a recycling process, and it can amplify the amount of felsic crust even if the initial production rate is low. All three mechanisms may have operated simultaneously. The Hadean Earth is not a simple system with a single mode of crustal formation, but a complex, dynamic environment where multiple processes contribute to the growth of continental crust. Some granite forms by subduction, some by underplating, some by remelting. The relative importance of each process changes over time as the mantle cools and the style of tectonics evolves. 3 different ways to make granite, and geologists can't agree which dominated, probably all of them, probably none of them exclusively. Ambiguity in the basement. The oldest known granitic rocks date to just after the Hadean, around 4.03 billion years ago. But the Jack Hill zircons prove that felsic magmas were forming by 4.4 billion years. The discrepancy arises because zircon crystallizes at high temperatures, early in the cooling history of a granitic magma. While the granite itself solidifies later, a zircon can record the time the magma formed, even if the granite that hosts it is destroyed by subsequent erosion or metamorphism. The zircons survive. The granite does not. This survival bias complicates the interpretation of the Hadean rock record. What is preserved is not necessarily representative of what existed. The granite bodies that formed in the Hadean have been almost entirely recycled or eroded away, leaving only their zircons as evidence. The granite that survives from the early Archean may represent only the most stable, most buoyant, most resistant portions of the early continental crust, while the less stable portions have disappeared without a trace. But the chemistry of the surviving granite is telling. Early Archean TTG rocks are distinct from modern granites. They are richer in sodium than potassium, and they have higher ratios of strontium to yttrium, consistent with formation by melting at high pressure, either in a subduction zone or at the base of thick crust. They also lack certain minerals, like garnet, that are common in modern granites but require specific pressure-temperature conditions to form. These chemical signatures suggest that the early crust formed under conditions somewhat different from today, perhaps in a hotter, thicker crust, or in subduction zones with different thermal structures. The accumulation of granite changes the planet. Once formed, granite is difficult to destroy. It is too buoyant to subduct, too resistant to erosion to be removed quickly, and too refractory to remelt easily. It accumulates at the surface, thickening the continental crust, building up the protocontinents, and creating landmasses that rise above sea level and persist for billions of years. Without granite, continents would not exist. The Earth would be a water world, covered entirely by ocean, with only volcanic islands rising temporarily above the waves. Granite is, in a sense, the foundation of terrestrial civilization. All the land animals, all the terrestrial ecosystems, all the continents and mountain ranges and river valleys that humans know are built on granite. It is the stage on which life's later acts will be performed, and it begins to form, slowly and quietly, in the Hadean, accumulating grain by grain, pluton by pluton, until there is enough to float permanently above the sea. The late heavy bombardment punctuates the cooling, around 9 billion years ago, perhaps a few tens of millions of years before the Hadean-Archean boundary. The inner solar system experiences a sudden increase in impact rate. The Moon's surface is saturated with craters from this period. The large, dark Maria, the seas visible on the Moon's face, are impact basins created during the bombardment, later filled with basaltic lava. Mercury, Mars, and presumably Earth are also heavily cratered during this time, though on Earth, the evidence has been erased by subsequent geological activity. The cause of the late heavy bombardment is debated. One leading hypothesis is the Nice model, named after the French city where it was developed. According to this model, the giant planets, Jupiter, Saturn, Uranus, and Neptune, form closer together and in a more compact configuration than their current orbits. Over the first few 100 million years of the solar system's history, gravitational interactions between the planets and the disk of planetesimals beyond Neptune gradually altered the planet's orbits. Eventually, around 3.9 billion years ago, Jupiter and Saturn crossed a 2:1 orbital resonance, Jupiter completing 2 orbits for every one of Saturn's, and this resonance destabilized the orbits of Uranus and Neptune, causing them to migrate outward. The outward migration of the giant planets scattered the planetesimals in the outer solar system, flinging some of them inward toward the Sun. This sudden influx of comets and asteroids created the late heavy bombardment, pelting the inner planets with impacts for perhaps 100 million years. The model is elegant and explains several features of the solar system's architecture, but it is not without problems. Some simulations predict bombardments that are too long or too intense, and the timing remains uncertain. The lunar samples that constrain the age of the bombardment are all from the Moon's near side, and there is debate about whether they represent a single event or the tail end of a longer, declining impact rate. An entire solar system rearranging itself just as Earth was trying to settle down. Took 400 million years to mostly solidify, then got pummeled. Timing. Whatever its cause, the bombardment is severe. Estimates suggest that during the peak of the late heavy bombardment, Earth is struck by perhaps 20 to 40 impactors larger than 100 kilometers in diameter, and thousands of smaller ones. The largest impacts create craters over 1,000 kilometers across, excavate millions of cubic kilometers of rock, and release enough energy to vaporize oceans and sterilize large portions of the planet's surface. But by this time, Earth is more resilient than it was in the earlier Hadean. The crust is thicker, more stable, less prone to complete remelting. The impacts create enormous craters, but they do not return the planet to a molten state. The crust fractures, melts locally, and is ejected into the atmosphere, but it does not flow and heal itself as it did during the early Hadean. The craters persist, at least for a time, as recognizable structures. Some of the impact melt from these craters may be preserved in the ancient rock record. Certain early Archean terrains contain anomalous layers enriched in platinum group elements, iridium, osmium, ruthenium, that are rare in Earth's crust but common in asteroids. These layers may represent fallout from large impacts. The vaporized remains of the impactors settling out of the atmosphere as a fine dust that later lithified into rock. The interpretation is tentative. Platinum group elements can also be concentrated by volcanic processes, but the association with shocked minerals and impact spherules in some cases strongly suggests an impact origin. The bombardment does not erase the progress made during the Hadean. The protocontinents survive. The oceans, if temporarily vaporized by the largest impacts, recondense within millennia. The atmosphere, though disturbed, settles back into a greenhouse-dominated state. But the bombardment does delay further development. Each large impact remelts portions of the crust, erases sedimentary deposits, and disrupts whatever chemical or geological processes were underway. The planet is repeatedly reset, forced to begin again from a state of local devastation. Rebuilding what was destroyed, the energy released by a large impact is difficult to comprehend. A 100-kilometer impactor striking at 20 kilometers per second releases approximately 10 circumflex 23 joules, roughly the energy output of the Sun hitting Earth for an entire week, delivered in a fraction of a second. The impact vaporizes the impactor and an equal mass of target rock. A fireball expands outward at supersonic speeds. The atmosphere above the impact site is blown away, creating a temporary vacuum that is then filled by air rushing back in. Ejecta is launched on ballistic trajectories, some of it reaching orbital velocities and escaping into space, some of it falling back to Earth thousands of kilometers away. The thermal pulse from the impact heats the atmosphere, rocks falling back through the atmosphere as ejecta radiate heat, creating a global infrared pulse that can ignite wildfires across entire continents. On the Hadean Earth, there are no forests to burn, but the heat is sufficient to boil surface water and to raise atmospheric temperatures by tens of degrees for hours or days. Any organisms living at the surface, if any organisms exist at this time, would be killed by the heat. But the deep ocean, if it exists, provides refuge. Water is an excellent thermal buffer, and organisms living even a few tens of meters below the surface would be shielded from the worst of the thermal pulse. Similarly, organisms living underground, in the pores and fractures of the crust, would be protected. If life originated before the late heavy bombardment, and the timing of life's origin is deeply uncertain, it may have been driven into refugia during the bombardment, surviving in isolated pockets and then recolonizing the surface once conditions improved. Impacts large enough to boil the ocean's surface, but not large enough to boil the whole ocean. Margin of survival measured in meters of water. Lucky depth. The late heavy bombardment also delivers material to Earth. Comets, rich in water and organic compounds, contribute to the planet's volatile inventory. Asteroids, some of them metallic, deliver iron, nickel, and platinum group elements. Some scientists have speculated that the bombardment may have delivered the building blocks of life, amino acids, nucleotides, lipids, though whether such molecules could survive the heat and pressure of an impact is unclear. Laboratory experiments show that some organic compounds can survive shock pressures equivalent to those of an impact, but the fraction that survives is small, and whether it is sufficient to jumpstart prebiotic chemistry is debated. The bombardment tapers off gradually. By 3.8 billion years ago, the impact rate has declined to something closer to its modern value, though still higher by an order of magnitude. The craters left by the bombardment begin to erode. Rivers cut through their rims. Sediment fills their floors. Volcanic activity buries them. Within a few 100 million years, most of the craters have been erased from the geological record, leaving only faint chemical and isotopic signatures to mark their former existence. The Hadean-Archean boundary, conventionally placed at 4.0 billion years ago, is somewhat arbitrary. There is no single event that defines it, no sudden transition from one type of planet to another. The boundary is chosen based on the age of the oldest surviving rocks, but those rocks represent a preservation boundary, not a fundamental change in Earth's behavior. The processes that operated in the late Hadean, volcanism, erosion, sedimentation, impact cratering, continue largely unchanged into the Archean. What does change is the stability of the crust. By 4.0 billion years ago, enough continental crust has accumulated to create stable cratons, regions that will resist subduction and erosion for billions of years. The rock record becomes continuous, or nearly so. The age of inference and extrapolation gives way to the age of direct observation, where geologists can examine actual rocks, measure their compositions, study their structures, and reconstruct the environments in which they formed. The bombardment is the last great obstacle to stability. Once it ends, the planet can finally settle into a more predictable rhythm. Volcanism, tectonics, erosion, sedimentation, the slow construction of continents. The stage is set for the next great transformation, the one that will eventually distinguish Earth from all other known planets, the origin of life. But that transformation is not immediate. The Hadean ends, the Archean begins, and the planet, still hot, still active, still barren, continues its patient work of building a surface that can be called solid, permanent, and ready for whatever comes next. Cratons lock into place. The term craton comes from the Greek word for strength, and it is apartment. Cratons are the ancient, stable cores of continents, regions of thick, buoyant crust that have resisted deformation, subduction, and erosion for billions of years. They are geological anchors, the oldest surviving pieces of Earth's surface, and they form the nuclei around which younger crust accretes over time. The oldest cratons, the Kapval Craton in South Africa, the Pilbara Craton in Western Australia, the Slave Craton in Canada, preserve rocks dating back to 3.7 or 3.6 billion years ago, and possibly older. These rocks are metamorphosed, their original features obscured by heat and pressure, but their ages and compositions are unmistakable. They are the survivors, the fragments of Hadean and early Archean crust that managed to persist through 4 billion years of geological tumult. What makes a craton stable? The answer is thickness and composition. Cratons have roots, deep keels of cold, dense lithosphere that extend perhaps 200 kilometers into the mantle, far deeper than the roots of younger continental crust. These keels are compositionally distinct, depleted in elements that have been extracted by melting, and they are colder and more viscous than the surrounding mantle. This makes them difficult to deform or to drag down into the mantle. They resist the forces that would otherwise recycle them, and so they persist. Crust so old it predates most of the planet's history, just sitting there, undeformed, outlasted supercontinents, mountain ranges, entire oceans, stubborn rock. The formation of cratonic keels is thought to be linked to the extraction of large volumes of melt from the mantle. As the mantle melts to produce the crust, the residue left behind is depleted in basaltic components and enriched in refractory minerals like olivine and orthopyroxene. This residue is less dense than the surrounding unmelted mantle, and it is also more viscous, which makes it buoyant and resistant to convection. Over time, this depleted residue accumulates beneath the thickening crust, forming a keel that stabilizes the craton and prevents it from being subducted or delaminated. The process is self-reinforcing. thick crust produces a thick keel, and the thick keel makes the crust even more stable, which allows it to accumulate more material, which thickens it further. Once a craton reaches a critical size, perhaps a few hundred kilometers across, it becomes nearly indestructible. It can be rifted apart, split into fragments, or buried beneath younger sediments, but it cannot be easily destroyed. The Karpval Craton is one of the best studied examples. It preserves rocks from the Barberton Greenstone Belt, dated to between 3.5 and 3.2 billion years ago, as well as older gneisses that may date back to 3.7 billion years. The Greenstone Belt contains pilobasalts, lavas that erupted underwater and cooled rapidly, forming rounded, pillow-shaped masses, as well as comatites, sedimentary rocks, and cherts. These rocks provide a detailed record of early Archean environments, and they suggest that by 3.5 billion years ago, the Karpval region had stable crust, a functioning hydrological cycle, and perhaps even early microbial life. The Pilbara Craton in Western Australia is similarly ancient. It contains some of the oldest well-preserved rocks on Earth, including stromatolites, layered structures formed by microbial mats that date to 3.5 billion years ago, and possibly older. The Pilbara rocks record a history of volcanism, sedimentation, and metamorphism, and they show that the craton has been stable for at least 3.5 billion years, surviving multiple episodes of tectonic activity, erosion, and deformation without being destroyed. The Slave Craton in northern Canada contains the Acasta gneiss, dated to 4.03 billion years ago, the oldest known intact rock on Earth. The gneiss is highly metamorphosed, its original structure almost entirely erased, but its age is confirmed by uranium-lead dating of zircons within the rock. The Acasta gneiss proves that by 4.0 billion years ago, felsic crust existed and was stable enough to survive into the present. A span of time nearly as long as the Earth has existed, a rock 4 billion years old. Still here, still mappable, still testable, older than mountains, older than oceans, older than oxygen in the air. The cratons are not static. They drift, collide, and sometimes rift apart over billions of years. They have been assembled into supercontinents and then dispersed multiple times. But the cratons themselves persist. They are the stable platforms on which the rest of the continents are built. The ancient cores that have witnessed the entire history of multicellular life. The rise and fall of countless mountain ranges, the opening and closing of ocean basins. By the end of the Hadean and the beginning of the Archean, several cratons have formed. They are small, each perhaps the size of a large island or a small country, but they are stable. They resist recycling. They accumulate sediments, host volcanic eruptions, and provide the stable platforms on which the first ecosystems will eventually establish themselves. The cratons also preserve Earth's oldest sedimentary rocks, and with them, clues about the early atmosphere, ocean, and climate. The sediments contain chemical signatures, iron oxidation states, carbon isotope ratios, sulfur isotope anomalies, that record the composition of the fluids from which they precipitated. By studying these signatures, geologists can reconstruct the conditions at Earth's surface billions of years ago, inferring temperatures, atmospheric compositions, and redox states. The Isua Greenstone Belt in Greenland, dated to 3.8 billion years ago, contains some of the oldest metasedimentary rocks, sedimentary rocks that have been metamorphosed but still retain some of their original features. These rocks include banded iron formations, cherts, and turbidites, indicating that by 3.8 billion years ago, the ocean was chemically active, depositing minerals in layered sequences that suggest seasonal or cyclic changes in water chemistry. The preservation of these rocks is remarkable. They have been buried, heated, deformed, uplifted, and eroded, yet they survive. They are windows into a time when the Earth was fundamentally different, when the atmosphere lacked oxygen, when the ocean was rich in dissolved iron, when the continents were small and scattered. They are archives, written in stone, of a world that no longer exists but whose legacy shapes everything that has come since. The cratons lock into place, the crust stabilizes, and the planet, for the first time in its history, has a surface that will endure, a foundation on which the next 4 billion years will be built. Greenstone belts archive the transition. These elongated, synclinal structures, typically tens to hundreds of kilometers long and a few tens of kilometers wide, are among the most important geological features of the Archean. They contain a mixture of volcanic and sedimentary rocks, metamorphosed but still interpretable, and they record the processes by which the early crust formed, evolved, and stabilized. Nearly every Archean craton contains greenstone belts, and they are the primary source of information about the Hadean-Archean transition. The name greenstone refers to the color of the metamorphosed volcanic rocks, which are often rich in chlorite, epidote, and actinolite, green minerals that form when basalt and comatite are subjected to low-grade metamorphism in the presence of water. The green color is distinctive, visible even in hand samples, and it gives the belts their name. Greenstone belts typically contain 3 main rock types: ultramafic lavas, comatites, mafic lavas, basalts, and sedimentary rocks, sandstones, shales, cherts, and banded iron formations. The volcanic rocks are usually at the bottom of the sequence, with sedimentary rocks on top, suggesting a progression from a volcanically active environment to a more quiescent, erosional environment. This progression is interpreted as recording the evolution of a volcanic arc or oceanic plateau that eventually stabilized, emerged above sea level, and began to shed sediment. But the exact tectonic setting of greenstone belts is debated. Some geologists interpret them as ancient subduction-related volcanic arcs, analogous to the island arcs that form above modern subduction zones. Others argue that they formed in rift settings, where the crust was being pulled apart and mantle material was rising to fill the gap. Still others propose that they are the remnants of oceanic plateaus, thick accumulations of volcanic rock formed by mantle plumes that were later accreted onto the edges of growing continents. Ancient volcanic sequences that could be arcs, or rifts, or plateaus, metamorphosed enough that the key features are ambiguous. Everyone has a model. No one has proof. The comatites in greenstone belts are particularly informative. Their high magnesium content and high eruption temperatures indicate that they formed by melting of a very hot mantle, hotter than the modern mantle by at least 200 degrees Celsius. This is consistent with a Hadean and early Archean Earth that was still cooling from its formation, still radiating away the heat of accretion and differentiation. The comatites also contain nickel sulfide deposits, formed when the hot lava dissolved sulfur from the surrounding rocks and then precipitated nickel-rich minerals as it cooled. These deposits are economically important today, mined for nickel used in stainless steel and batteries. The sedimentary rocks in greenstone belts are equally important. They include cherts, fine-grained siliceous rocks that precipitate from silica-saturated water, and banded iron formations, which consist of alternating layers of iron-rich and silica-rich minerals. Banded iron formations are diagnostic of Archean and Proterozoic oceans, which were rich in dissolved ferrous iron, Fe2+, due to the lack of atmospheric oxygen. When cyanobacteria began producing oxygen, the oxygen reacted with the dissolved iron, precipitating it as insoluble ferric iron, Fe3+ oxides. But in the Archean, before oxygenic photosynthesis evolved, iron could accumulate in the ocean, and it precipitated in rhythmic layers, possibly driven by seasonal or volcanic changes in ocean chemistry. The presence of banded iron formations in greenstone belts indicates that by 3.8 billion years ago, the ocean existed, was chemically stratified, and was actively precipitating minerals. It also indicates that the ocean was anoxic, lacking in dissolved oxygen, which is consistent with an atmosphere dominated by carbon dioxide, nitrogen, and possibly methane, with little or no free oxygen. The sedimentary rocks also contain detrital zircons, zircon grains that have been eroded from older rocks and deposited in younger sediments. By dating these zircons, geologists can determine the age of the source rocks, even when the source rocks themselves no longer exist. Some detrital zircons in Archean greenstone belts have ages of 4.0 to 4.4 billion years, proving that felsic crust existed in the Hadean and was being eroded by rivers and deposited in sedimentary basins. Zircons older than the rocks that contain them. Fragments of a vanished world, recycled into a younger one. Orphaned crystals. The metamorphism of greenstone belts complicates their interpretation. Most greenstone belts have been subjected to green schist or amphibolite facies metamorphism, conditions of moderate temperature, 300 and 600 degrees Celsius, and pressure, 310 kilobars, which alters the mineralogy and texture of the rocks without completely erasing their original features. Original volcanic textures, such as pillows and spinifex, are often preserved, but the minerals have been replaced by metamorphic equivalents. Some greenstone belts have been more intensely metamorphosed, reaching granulite facies, temperatures above 700 degrees Celsius, and in these cases, the original features are largely destroyed. The rocks become gneisses, banded, high-grade metamorphic rocks, and their origin as greenstone belts can only be inferred from their bulk chemistry and their association with less metamorphosed rocks nearby. The structure of greenstone belts is also informative. They are typically synclinal, folded into downward opening troughs, suggesting that they have been compressed horizontally, possibly by tectonic forces related to collision or subduction. The folds are often tight, with limbs that dip steeply or are even overturned, indicating significant strain. This deformation is consistent with the idea that greenstone belts formed in tectonically active settings, where crustal blocks were colliding and volcanic arcs were being accreted onto the margins of growing cratons. But the deformation also makes it difficult to reconstruct the original geometry and extent of greenstone belts. What is now a narrow, elongated belt may have originally been a much larger volcanic province, later compressed and attenuated by tectonic forces. The original thickness of the volcanic pile is uncertain, and the lateral continuity of individual lava flows or sedimentary layers is often impossible to determine. Despite these challenges, greenstone belts remain the best archive of early Earth processes. They record the transition from a planet dominated by volcanic activity to one with stable continents, functioning hydrological cycles, and sedimentary basins. They preserve evidence of the high-temperature mantle that characterized the Hadean and early Archean, and they provide the context for understanding the origin of life, which may have occurred in hydrothermal systems associated with greenstone belt volcanism. Though direct evidence remains elusive, the greenstone belts are libraries written in metamorphosed stone, their pages folded and torn, their text partially erased, but still readable to those patient enough to decipher them, a surface that can be carved by 3.8 billion years ago, perhaps earlier. The Earth has crossed a threshold. The crust is solid, thick, and stable. The oceans are present, liquid and chemically active. The atmosphere, though still very different from today's, has stabilized at a lower temperature. And for the first time, the surface is cool enough, rigid enough, and persistent enough to support true erosion, the gradual wearing away of rock by wind, water, and ice, and the transport of the eroded material to new locations where it accumulates as sediment. Erosion is a slow process, but it is relentless. Rain falls on exposed rock. Water seeps into cracks and fractures. Chemical reactions dissolve soluble minerals. Feldspars break down into clays, releasing sodium, potassium, and silica into solution. Physical weathering breaks the rock apart, freeze-thaw cycles. If ice is present, or thermal expansion and contraction as the surface heats and cools, the broken fragments are washed down slope by running water, carried by rivers, and deposited in lakes, deltas, and shallow seas. The first landscapes are volcanic. Lava flows, volcanic plateaus, and broad shield volcanoes dominate the topography. There are no high mountain ranges yet. The crust is too hot and weak to support them. But there is relief. There are highlands and lowlands, slopes and valleys, places where water flows and places where it pools. And this topography is enough to drive erosion. The first rivers are short and steep. They cut V-shaped valleys into the volcanic rock, transporting sediment from the highlands to the lowlands. The sediment is coarse, sand and gravel. Fragments of basalt and comatite, not yet broken down into fine clay. The rivers deposit this sediment in alluvial fans and deltas, building up layers that will eventually lithify into sandstone and conglomerate. Rivers carving bedrock, sediment piling up in basins. Geography that persists long enough to have names. If anyone were there to name it, took 3.5 billion years. The ocean is the ultimate sink for eroded material. Rivers carry dissolved ions, sodium, calcium, magnesium, silica, into the ocean, where they alter the water's chemistry. Some of these ions precipitate out as minerals, carbonates, clays, silica, forming chemical sediments. Others remain in solution, gradually increasing the ocean's salinity. The modern ocean is salty because of billions of years of this process. Billions of years of rivers dissolving minerals from the continents and transporting them to the sea. But the early ocean is different. It is less salty because there has been less time for salts to accumulate. It is more acidic because the atmosphere contains more carbon dioxide, and it is chemically reducing, rich in dissolved ferrous iron and other reduced species, because there is no free oxygen to oxidize them. This reducing ocean is capable of dissolving and transporting metals that would precipitate out in a modern, oxygenated ocean. And this leads to the formation of distinctive sedimentary deposits, such as the banded iron formations found in Archean greenstone belts. Erosion also shapes the continents. As the highlands are worn down, the sediment is deposited in the lowlands, gradually filling in the topography and creating more level terrain. Over time, the relief decreases. The continents become flatter, broader, more stable. This process, called peneplanation, creates vast, low-lying plains that are resistant to further erosion. Some of these ancient peneplains still exist, preserved in the interiors of cratons, their surfaces barely modified in billions of years. But erosion is balanced by uplift. Tectonic forces, whether driven by mantle plumes, by plate collisions, or by other mechanisms, continue to raise the crust, creating new topography to be eroded. The balance between uplift and erosion determines the long-term evolution of the continents. If uplift exceeds erosion, mountains grow. If erosion exceeds uplift, mountains are worn down. The two processes are in constant competition, and the landscape is the record of their interaction. Weathering also affects the atmosphere. When silicate minerals weather, they consume carbon dioxide from the atmosphere, incorporating it into carbonate minerals that are eventually buried in sediments. This is the silicate weathering feedback, one of the most important climate-regulating mechanisms on Earth. By removing carbon dioxide from the atmosphere, silicate weathering reduces the greenhouse effect and cools the planet. Over geological time, This feedback helps stabilize Earth's temperature, preventing runaway greenhouse warming or cooling. In the Archean, with higher atmospheric carbon dioxide levels, silicate weathering is more intense. The rate of weathering is proportional to the concentration of carbon dioxide, so a high CO2 atmosphere drives rapid weathering, which removes CO2 from the atmosphere, which slows the weathering, creating a negative feedback loop that tends to stabilize atmospheric CO2 at some equilibrium value. Rocks weathering, consuming carbon dioxide, regulating the climate, a planetary thermostat made of stone and rain, operating for 4 billion years without maintenance. The carved landscapes are also the sites where life, if it exists, is most likely to be found. Hydrothermal systems, hot springs, submarine vents, geysers are common in volcanically active terrains, and they provide energy and chemical gradients that may have been important for the origin of life. Shallow pools on volcanic plateaus, warmed by the sun and enriched in dissolved minerals, may have been prebiotic reactors, sites where organic molecules could accumulate and react. River deltas, with their fluctuating water levels and diverse microenvironments, may have provided niches where early life could gain a foothold, but direct evidence of life in the Hadean is absent, and in the early Archean, it is ambiguous. The oldest putative fossils, microbial mats and stromatolites from the 3.5 billion-year-old rocks of the Pilbara and Kap Vaal cratons are controversial. Some scientists accept them as genuine biological structures. Others argue that they could be formed by abiotic processes, such as mineral precipitation in rhythmic layers. The debate is unresolved, and it may remain so until better preserved specimens are found or until new analytical techniques can definitively distinguish biotic from abiotic structures. What is clear is that by 3.8 billion years ago, the Earth has a surface capable of supporting life, should life arise. There is liquid water, chemical energy, diverse environments, and stable substrates. The stage is set. Whether the first act has already begun, or whether it is still waiting in the wings, is unknown. The surface can be carved, the rivers flow, the sediments accumulate, and the planet, no longer molten, no longer chaotic, settles into the long, slow work of geological evolution, building continents, cycling elements, shaping landscapes, and preparing, without intent or purpose, for the emergence of something entirely new. The motion slows. The plumes rise less vigorously. The convection cells widen, their circulation becoming languid, almost imperceptible over spans of millions of years. The heat that once drove the planet's restless transformation now escapes more slowly, radiating into the emptiness of space at a rate that decreases century by century. Eon by eon. The mantle cools, the crust thickens, the surface, once molten and flowing, becomes rigid, becomes stable, becomes something that can be called, without ambiguity, solid ground. The impacts have ceased, or nearly so. A few stray asteroids still strike the planet, carving small craters that erode away within a few million years. But the great bombardments are over. The solar system has cleared itself of debris. The remaining asteroids orbit in stable regions, the asteroid belt, the Kuiper belt, far from the inner planets, and they will remain there, largely undisturbed, for billions of years to come. The sky is quieter now. The nights are darker. The moon continues its slow recession, pulling away from the Earth at a few centimeters per year, a pace so gradual that 100 million years pass before the distance increases noticeably. The tides weaken. The day lengthens. The planet's rotation, once frenetic, settles into a more measured rhythm. 6 hours becomes 12 hours becomes 20 hours. The progression spanning billions of years, and still the moon drifts outward. Still the tides slow, patient and inevitable. The protocontinents have merged, fragmented, and merged again, beginning the long dance of continental drift that will continue for the rest of Earth's history. Supercontinents will form and break apart. Oceans will open and close. Mountain ranges will rise and erode away. All of this over timescales so vast that the entire span of human history would be invisible. A flicker too brief to register in the geological record, but that is later. For now, the continents are small, scattered, and quiet. They float on the mantle like rafts on a slow-moving sea, drifting at speeds measured in millimeters per year, colliding with the softest of impacts, their edges folding and thickening rather than shattering. There are no earthquakes in the modern sense, no sudden ruptures, only the continuous, imperceptible deformation of rock under pressure, the slow buckling of crust over millions of years. The surface is carved, but gently. Rivers flow, but they are small and lazy, meandering across low-relief terrain, depositing sediment in thin, even layers. There is no hurry. There is no urgency. The planet is building its archive, page by page, layer by layer, each stratum recording a moment in deep time, and the archive will grow until it spans billions of years, until it contains within itself the entire history of the Earth. The first stable crust has formed. The Hadean is ending, or has ended. The boundary is indistinct, a matter of definition rather than observation. The Archean is beginning, or has begun, and it will last for more than 1 billion years, a span longer than the time from the Cambrian explosion to the present, longer than the entire Phanerozoic. But that, too, is just a chapter in a much longer story. The zircons rest in the sediments, tiny and indestructible, carrying their isotopic memories forward through time. The cratons stabilize, their deep roots anchoring them against the forces that would otherwise recycle them. The green stone belts fold and metamorphose, preserving their volcanic and sedimentary sequences in altered but still interpretable form, and the planet, cooling slowly, turning slowly, drifting slowly through the void, settles into a stillness that is not the absence of motion, but the presence of patience. Geological time is not empty. It is full of incremental changes, full of processes operating at rates too slow for any human observer to perceive, full of transformations that require millions of years to complete and billions of years to appreciate. The formation of the first stable crust is not a moment but a process, stretched across hundreds of millions of years, and it is already giving way to the next process, and the next, and the next, each building on what came before, each preparing the ground for what will come after. The surface is solid now. It can be walked upon, though nothing walks. It can be carved, and it is being carved, grain by grain, layer by layer. It will endure, not forever, nothing endures forever, but for long enough. Long enough to host oceans and atmospheres and ecosystems and civilizations. Long enough to be, in every meaningful sense, a world. The planet rests. The deep stillness of geological time settles over the surface like a blanket. And in the silence, in the darkness, in the vast, patient expanse of the Archean, the Earth continues its work, building, eroding, cycling, transforming, preparing. Sleep well.